Hello again. What we're going to do today is do a normal approximation to the binomial problem. And this particular one is number 27 off of page 321 in the textbook. And it says, according to Mars, the candy bar company, not the planet, our author is really funny, 24% of M&M plain candies are blue. So data set 18 in Appendix B shows that among the 100 M&Ms chosen, 27 of those are blue. So assuming that the claimed value from Mars, 24%, is correct, find the chances of randomly selecting 100 M&Ms and getting 27 or more that are blue. Okay? So what we want to do is first define a random variable. So B is the number of blue we get out of this draw of 100. And B, we know something about its distribution. You can check the 4 criteria, but it's binomial. And remember, this isn't the mean and the standard deviation. When you define a binomial random variable, this is n and p. So n is 100 trials, and p is 0.24. That's the 24%. But you want to write it as a probability, number between 0 and 1. So what do we know about the approximate distribution of b, which is what we're trying to do in this problem? Well, the approximate distribution is going to be normal, and the mean is just going to be, so the average of b is just n times p. So in our case, n times p is 100 times 0.24, which is 24. Okay? So the average is 24, and the standard deviation is, we call this sigma b or something like that, is the square root of n, which is 100, times p, which is 0.24, times 1 minus p, or q, is 0.76. And so when you get an approximation with that, it's 4.2708, I believe. So I'll write 4.2708. And remember, you can't just always arbitrarily choose to do this for a binomial random variable. You have to check 2 things. So we'll say because of 2 things. 1, because n times p is greater than 5, and 2, n times 1 minus p is greater than 5. These are the cutoff that are used in our textbook. Sometimes people use 10 as the cutoff. It doesn't really matter. 5 will work probably okay. 10 maybe be a little better though. So in our case, n times p is 24, which is obviously greater than 5, and n times 1 minus p would be 76, which is okay as well. So because these 2 conditions are met, we're allowed to use this approximation. Okay? So now let's go ahead and see if we can solve the problem that we're asked to do. We want to know the probability, if you do a random draw of 100, what's the probability that you get more than 27 or more blues? So this is what we're trying to find. Okay? We're asked to use that normal approximation, so what we're going to do is this. We'll say this is approximately equal to the probability that b approx is greater than or equal to, I don't want to use 27 here because we're going to use the continuity correction. And anytime you use a continuous distribution to approximate a discrete distribution, you end up getting better results if you use the continuity correction. And so we want to use 26.5 here. Okay? And so b approx is normal, at least approximately normal. So we can just go ahead and standardize this and solve this in our usual ways. So we'll go ahead and standardize it. B approx will subtract its mean, which I think we called mu b, and we'll divide by its standard deviation, which we called sigma b. And this thing will be at least approximately a normal 0, 1. So we'll do the same thing over here for the 26.5. We'll subtract, if we have to go to the other board here, it was 24 and 4.2708. So we'll subtract 24 and 4.2708. So because we took something that was at least approximately normal and standardized it, we'll get a z random variable, where z is a normal 0, 1. And over here, we'll take 26.5 minus 24 divided by 4.2708, so let's go ahead and see if we can simplify that. 26.5 minus 24, and we'll divide by 4.2708. So you get 0.5854. Okay, and so we want to know the probability that a normal 0, 1 is bigger than 0.5854. If you just use the table in the back of your book, we're going to have to round this to 0.59. So 2776 is what you end up with if you just use the table in the back of your book. That's is the best you can do. Let's go ahead and see if we can use StatCrunch to do a little bit better. So we'll just wait while the overhead projector warms up. And again, we get to StatCrunch through the link in Moodle. And that's the way for when you do your exams in the testing center, you're going to have to do it that way as well. So we'll go ahead and do stat, calculator, normal. And let's go ahead, if you put in a normal 0, 1 and you find the area greater than or equal to 0.59, so we'll do the greater than or equal to 0.59, we should come up with something pretty close to what we got out of the table in the back of the book, 2776. Here it's 277595, so that's pretty close to 0.2776, and that's where they got that. If we wanted to do a little bit better, I think this is probably what my stat lab wants, but you'll need to experiment with that. I try it sometime in your homework, and I think they want you to use the table. So, but you could also use this method to get table values. That would work as well. You could also say that this thing is approximately normal with mean 0.4. Now we're going back to B approx, and it has 4.2708. And we want to find the probability that it's bigger than 26.5. So this should give us a more exact type of value, which is 2791. Okay. Notice it's not very different. It's almost the same, but it is a little bit different. This would be a little more exact than what we had before. In terms of the follow-up question the book asked, they said, based on these results, is 27 an unusually high number of blue M&Ms? I don't think so, because 27%, almost 28% of the time, you're going to get at least 27. So that's I would not quantify that as being especially unusual, at least according to this. So next time we're going to look at how we can assess normality in StatCrunch, but that's it for this lesson.